Now it's time to analyze some relational graphs. We'll begin with the first one on the left, which consists of just 5 ordered pairs. I need to emphasize, those 5 ordered pairs are not connected by line segments or curves. Therefore, there are no points in between. And I can still, however, test to see if it's a function. Passes the vertical line test, passes the vertical line test, passes, passes, passes. In these cases, they only cross at most once, and therefore this is a function. Now when I look for the domain, I'm looking for all the x coordinates that are defined. And I can see one at -6, I can see one at -1, another one at 1, another one at 2, and then finally another one at 5. In this particular case, I do not want to write as an interval because I'm not connecting from -6 to 5. I only have these 5 values, and I'll just write it as a set notation of those 5 values. Range is all about up and down. It's all about y-coordinates. And I have a y-coordinate -4, I have one at 0, I have one at 1, one at 2, and one at 5. Those 5 values are the only 5 values in my range. Do not write it as an interval because they're not connected height-wise. Now if I'm trying to find f of -5, you want to go to where x equals -5. You kind of want to look on this line and see where is defined on that point. But I don't see any points. And if I don't have any points that I can see, then I'm going to have to assume that it's undefined at this value, which is a little different when I do x equals 5 because I can go right to here and see, I do have a point at x equals 5. It happens to be at a height of 1. Therefore, f of 5 equals 1. The graph on the right is an oval. I can tell pretty much immediately that it's going to fail the vertical line test. And if it fails the vertical line test, it is not a function. Now, what I'm interested for the domain is to try to figure out all the values of x's that are being graphed. The graph doesn't go any farther back from -1. It doesn't go any farther to the right than 3. But it may be going down, but it is still connecting from -1 to 0 to 1 to 2 to 3. In fact, all these points in between are included as part of the domain. And this one could be written as interval notation, or it could be written as -1 is less than or equal to x, which is less than or equal to 3. Because -1 and 3 are included, I need to use brackets for my interval notation. Now my range is all about y-coordinates. And this graph goes as low as -4, and it goes as high as 2. But it does connect all the heights. So everything from -4 to 2, including the endpoints, would be part of my range. And I can write that also as -4 is less than or equal to y, which is less than or equal to 2. Now when I go f of 1, okay, I'm saying x equals 1. But there's a problem here. I have a point here, and I have a point here. And if you recall, this is not a function for exactly that reason. You cannot be using f of 1 because that's function notation, and this is a non-function. So that should never have been used to begin with. 2 more examples of graphs. We'll begin with the one on the left, and we can see that that graph looks like it's going to pass the vertical line test. I'm just going to draw some vertical lines. It seems to cross no more than once, so yes, this is a function. Now this graph, although it looks like it stopped here, I can assume it's going to keep going this way. In fact, I will assume that it will keep going to the left forever. Just like even though the graph gets cut off here, I would assume that this is going to keep going forever, and we already know that everything's being connected from left to right. Therefore, the domain will be all reals. The range, on the other hand, it seems that the highest the graph goes is at 5. But the graph does keep going lower and lower and lower forever. So I guess you could say it starts at -infinity and goes up to 5, which I can write easily in an interval notation. Just make sure I use a bracket for the 5. Or I can just say y is less than or equal to 5. If I'm trying to find f of -3, I'm just going to go to -3, which is right here, look for the point. Okay, there's my point there. And then what value of y comes out? Well, in this case, that value of y is -4, and that's what f of -3 equals. It equals -4. The graph on the right is what might be known as a piecewise function. It's made up of different pieces. seems to be a little confusing, but it still passes the vertical line test. It only crosses once here. It only crosses once here. The issue is what happens specifically at 0. I can tell you this. Because of the hollow dot, this is not included. This hollow dot's not included. But this dot is included. And right at this moment, it only crosses one solid point when x equals 0. And so if all the negatives are included and all the positives are included and 0 is included, then not only is this a function, but the domain is all reals from negative infinity to infinity. Now on the other hand, let me erase a lot of this. Oops, that was supposed to be an eraser. On the other hand, if I'm asking you what the heights are, well, that's a different story. In fact, all I see right now is that there's a height at -2, and it's pretty much all the values that are negative. There's heights at 2, which are all the values of positive x. But there's also a height of 0 when x specifically is 0. Those are the only 3 values that seem to come out. Those are the only 3 values in my range. Do not try making an interval notation. If you did, then you would be saying that there could be values of 1.5 or -0.5 that come out, and they don't. Only 3 values come out. Remember I said f of 0, or I said x equals 0? Well, f of 0 is going to be that one point and that one point alone's height, and that height happens to be 0. Meanwhile, x equals 6, well, it happens to be a height right here at 2, and therefore the value that comes out is 2. Finally, we come to an application of relations and functions. In this particular example, we're going to keep it relatively simple. We're just going to basically get prints made, and we want to know what the cost is. Or we have the cost, we want to know what the number of prints made. And that's really what the basis of this question is. Which is traditionally true? Is cost a function of prints made, or is prints made a function of cost? Let's emphasize the phrase a function of. If I'm going to draw this, and I'm going to draw this twice, I'm going to call this number 1, and I'm going to call this number 2. The top one is number 1. This is option number 2. If you're saying cost is a function of prints made, you're saying cost is your output. That will represent your range, your dependent variable. And prints made is going to be your input. On the other hand, if you're saying prints made is a function of, you're going to say prints made is your output and cost is your input. Now, what is considered to be usually true? Well, here's how you have to sort of look at it. Is this a case where, I know I have 40 prints. I wonder how much that's going to cost me. If that's the way you're looking at it, you've just done option number 1. You have established that you had 40 prints, and now you need to determine the cost. On the other hand, there are times like I have all these prints, but I only have $1.50. I wonder how many prints I could make. Now, cost is sort of dictating the rules of what you're going to do, and this would be an option for number 2, where you put in the cost and it will determine how many prints made. What you're going to find out in a later lesson is essentially that these statements are inverses to each other, but I'm not going to go there right now. I would say more often than not, people will say, oh, I have these prints, how much will it cost me? And that's why you'll say cost is a function of prints made. But the moment you let cost dictate what you're going to do, I only have $3, I wonder what I can do with that, that becomes your independent, and then prints made is the dependent. But we're going to stick with the original, cost is a function of print made. And because you're saying prints made is what's going up, so we're going to say it's this option right here, then your independent variable is going to be prints made, and we'll call that the letter P. And since the output is cost, we'll have to define that to be our dependent variable. We'll call that the letter C. So if I'm asked to come up with an equation in function notation that represents a situation, well, first off, you have to remember that the function notation is going to start off with the dependent variable. It's going to be the letter C. But I need to have the input of the independent variable. So my equation is going to start off as C of P. Then I just need to have some expression right here where I use the value of P to come up with an overall cost. And since literally it's 15 cents per print, well, there's my 15 cents per print times the number of prints. Technically, you cross them out, and you're left with cents as your overall unit, and that's why it's C of P. And that is an example of function notation for a very simple example.